we are starting optimization, and it's a fun topic. It's not something I spend a lot of time on usually, but I do love how it kind of connects some stuff that you did in like Algebra 2, even Algebra 1. And now we just kind of make it beautiful with calculus, and it's super easy to solve. You will need your calculator for a couple of these examples, and some of them will be no calculator. So I guess it always depends upon how difficult it is if I want you guys to use your calculator or not. So optimization, let's talk about what that means. A farmer wants to fence in a rectangular field. He has 500 feet of fencing to use. One side of the field runs along a building, so no fence is needed on that side. Determine the dimensions of the field that would yield the largest area. So that's the maximum. Oh my goodness. Does that happen literally every time? It's like almost embarrassing. The largest area is the maximum area. Okay. Maximum. We just talked a lot about relative max and mins. I wonder if that has anything to do with these types of word problems. We're trying to optimize something, and in this case, we're trying to optimize the area, right? We want the largest possible area. So we know a little bit about the perimeter because we have 500 feet of fencing to use, but we really want to maximize the area. So let's draw ourselves a picture right here. So let's say this is my building. Okay, and I have some fencing. All right, I'm going to call this Y. I'll call this Y because I could use length and width. I'll just use X and Y. So I know the area enclosed is going to be X times Y. All right. And I also know that, let's see, I know that 2Y plus X is equal to 500, because if I'm optimizing or maximizing this area, I want to use every bit of fencing that I have. I can have my answer key out in front of me. Okay. So I know that a maximum is going to occur when the derivative of the area is equal to 0. My issue is right now is that my area is written in 2 different variables, and I don't love that. But I could use this secondary equation here that I know about the perimeter to get this equation into one variable. And I'm going to do that. I'm going to solve for X. So X is equal to 500 minus 2Y. You could solve for Y. You would just have fractions. I don't feel like dealing with fractions right now. And I'm going to rewrite the area. So I haven't even found the derivative yet. So it's going to be Y times 500 minus 2Y. And I'll distribute because I don't feel like doing the product rule. So this is 500Y minus 2Y squared. Well, I'm sorry. This is like such an easy problem. So, all right, let's rewind a second. So we're going to use calculus. You guys probably know what I'm going to do. I'm going to find the derivative. I'm going to set it equal to 0, and I'm going to see where the maximum takes place. Easy peasy. Back in like Algebra 1, at least I hope you did this in Algebra 1 or Algebra 2, you'd get a problem like this, same exact wording, and you would be able to do it then too, but you didn't know the calculus behind it. Instead, when you got to this point, you would graph this in your calculator and try to find, and you would find the maximum. This is a parabola, guys. And we would find the maximum, and we would locate the maximum on the calculator by doing second calc, and we'd hit maximum, and we'd get the answer. We don't need that anymore, okay? Instead, I can find the maximum of this function. The maximum of this function occurs when the derivative is equal to 0. So let's find the derivative. So that's 500 minus 4y. All right, so then I want to know where is the derivative equal to 0. So that's 4y equals 500. So y is equal to 125, and that would be what, feet? Never want to forget your units. So this is 125, which would make this be 125. So how much do I have left over then for this width or this length here? What, 250? Yeah. So, and then I always go, once I get like my answers, I go back and I make sure that I have found exactly what they're looking for. Because sometimes they're going to say, oh, what's the maximum area? And I didn't find that yet, right? The maximum area would be if I had to multiply these two together. Instead, they're saying, okay, determine the dimension. So I do have that. So let's just say maximum area takes place at 125 feet if we have a rectangle by 250 feet. So that's what's going to yield our maximum area. And guys, if I had gotten more than one answer here, I would have needed to think a little bit more, maybe with a sign chart to figure out what's a maximum, what's a minimum. But this one was super easy because it's a parabola. It has one maximum. Very easy. So I didn't really need to do any secondary work there to try to determine if my answer was actually correct or not. I knew it was. All right, easy peasy. Easy peasy maximum problem or optimization problem. Okay, next one, open top box. All right, an open top box will be made from a rectangular piece of cardboard. All right, let's draw this. So hopefully you guys can visualize this. Usually I'll cut this out if we're in school because there's always someone that doesn't visualize it. So we're cutting out corners from this piece of cardboard. And then once I fold up, I have a box, right? That would actually be able to hold something. If like I taped those sides up, once I fold them up and in, if you need to get yourself a piece of paper right now and cut out some corners, go ahead and do it and see that a box would be formed with no top on it, obviously. That's why, hence why it's called an open top box. All right, so let's see. I just drew my picture. Let's label it. The rectangular piece of cardboard is 8 inches by 5 inches. It will be made by cutting a square, the side length of X. So this square, this is a square, and that every single one of those squares has side length of X. From each corner and folding up the sides. Find the value of X that maximizes the volume. So I'm just looking for the height, really. Because think about it. When you fold this up, this right here ends up being your height, right? That's going to be the part that's above or that's standing up. So that's what I'm looking here. This is just a box, so I know how to find the volume of a rectangular prism. It's length times width times height. And let's figure out, okay. So here, once I cut out these corners, my length isn't 8 anymore, right? If this is X and this is X, and I cut those pieces out, this is the new length of of the open top box, and we get what? 8 minus 2X. I'm taking away 2 X's. And then the same thing's going to happen over here. The width isn't going to be 5 anymore. It's going to be 5 minus 2X, because this would be X and this would be X. So that did make me think a little bit, but I have everything in terms of X. There's like no substituting in like I had to do in the last example. So let's see. The volume is equal to length. I guess I should, it doesn't matter. So X times 8 minus 2X times 5 minus 2X. So I don't really feel like doing a triple product rule, so I'm going to FOIL this. I'm going to leave the X out for a second. So what's that? 40 minus, am I getting minus 26? Yep, minus 26X plus 4X squared. And again, I don't want to use the product rule. Again, that's just preference on my end. Some of you might say product rule's fun here, Mrs. Bucko. Let's go ahead and do it. That's a squared C. Okay, plus 4X cubed. Is that what I have in my paper? Yes, it is. Okay. Now I'm ready. So if I want to find the value of X that maximizes the volume, I'm looking for a maximum. So I know maximums occur when the derivative is equal to 0. So let me find the derivative. And because I'm crazy, I'm going to do this in descending order. So I'm going to work backwards. So that's going to be 12X squared minus 52X plus 40. Yes. I'm going to take out a GCF, so I want to set this equal to 0. I'm going to take out a 4, and I'm left with 3x squared minus 13x plus 10, and now this is factorable. I know it has to be 3x and x. This would need to be negative, this would have to be negative 1, and this would have to be negative 10. Did I do that correctly? 3, no, I didn't do that correctly because I want the 3 to multiply by the 1. So this would be, I always do guess and check for factoring. I don't know if you guys tend to use grouping. It always depends upon what you were taught in Algebra 1. I always like guess and check because I look what I did there. I took a guess and I checked it and it was wrong. And it took me 2 seconds to fix it. So now I have my 2 solutions. Two solutions. I want to know the value that's going to maximize my volume. So when I get 2 solutions like this, like in the last problem, I said it was totally fine that we got 1 solution because we knew that had to be it. And now I have 2 solutions and I've got to figure out which one is actually the right one. So I call it using common sense. I'm going to take a look at my side lengths and I'm going to take the smaller one. So 5 minus 2x. If I plug in 10 thirds here, 5 minus 20 thirds, I get a negative side length, right? So I know that this is not an acceptable answer because I can't have a negative side length. So the value of X that maximizes my volume is 1. X equals 1, and that's an inch. That's going to give me the maximum volume for that open top box. All right. Again, in Algebra 2, you would have just plugged this into your calculator. You would have found an appropriate window and found the maximum. Pretty cool. All right. Number 3. What's this? Oh, I like this one. A poster is to contain 100 square inches of picture surrounded by a 4-inch margin at the top and bottom and a 2-inch margin on the side. So I'm going to try to draw this somewhat accurately. All right, so that's my poster. If it was 7th grade Mrs. Bucko, it would be a poster of Justin Timberlake right there. Daddy? And now I wonder, what did I ever see in that guy? But I was convinced, and my husband is rolling his eyes at me right now. I was convinced in 7th grade that I was going to marry that guy. Good old NSYNC. So I've got 2-inch margins on the left and right and 4-inch margins on the top and bottom. All right, so I want to find the overall dimensions that minimize, so not maximum, but that's okay. Minimums and maximums both occur when the derivative is equal to 0. So it's still the same idea. Find the overall dimensions that minimize the area of the entire poster. So that's border and inside picture of Justin Timberlake. So we know that this area right here is 100 square inches, but I don't actually know the length and the width of that. I'm going to call that, oopsies, I'm going to call that X and Y. I'll have this one that's going across X, and I'll have this one, the height be Y. Okay, so that's Y, and then X is going across. Okay. All right, so let's figure out what we're supposed to do here. We want to find that minimize the area of the entire poster. So what I do know is that the area of the inside part is 100 square inches. So I do know that X times Y is 100. And I know the area of the entire thing. So now this whole length, so just take a look at how I labeled this. 4 plus 4 plus Y. So that's going to be 8 plus Y, or Y plus 8 if you want to write the variable first. And this would be X plus 4 because it's got 2-inch margins on both sides. So I can now write that the area of the entire thing is Y plus 8 times X plus 4. And again, I'm in 2 variables. It's ugly. I'm going to substitute in. So I'm going to choose to say that Y is equal to 100 over X. Again, it doesn't matter how you do this. You could do X equals 100 over Y, and we're going to get the same exact answer. So I'm going to sub in now. Why not? You could even write 100x to the negative 1 if you would rather. Just for derivative purposes later. I'm probably going to switch it in a little bit. So when I FOIL this, I still haven't taken the derivative. So when I FOIL this, I get 100 plus 400 over X. And that I should probably write as X. I'm going to do that. I'm going to write it as X to the negative 1 because I'm going to want to take the derivative in the next step. 400 X to the negative 1 plus 8X plus 32. I don't want to take the derivative. I want to combine like terms. 400 X to the negative 1 plus 8X plus 132. Again, why did I even care? When I take the derivative of a constant, it's 0. I should have just not done that step. But I'm crazy. All right, A prime. So that's what? Negative 400 over X squared. So it'd be X to the negative 2. I'm changing it back to a fraction. Plus 8. So I want to know, where is this equal to 0? Because that's where I'm going to have a minimum. I'm going to come work over here. So 0 is equal to negative 400 over X squared plus 8. So negative 8. Actually, no, I'm going to bring the others over to make everything positive. So I'll do 400 over X squared is equal. Oh, so we'll use a calculator for this one. Is equal to 8. 400 equals 8x squared. I actually, we could do this and get radicals as our answer, which if you look at my answer key online, I do keep it in radical form. I actually kind of just prefer to see decimals here so I can actually see the dimensions. And it's much easier for me to visualize than to look at radicals. So the reason I left it as radicals is because it's an easy one. Wouldn't that be 5 radical 2? And obviously we want the positive version of it, so I don't need to write plus or minus. But I'm going to actually get this into a decimal because I feel like it. 5 radical 2 is 7 point, and remember guys, 3 decimal places for credit, 7.071. We've got to start doing this. So we get full credit. And that would be what, inches? So then my y, I'd have to do 100 divided by that, right? So then my y is 100 divided by x, which is 14.142. And that would also be inches. So let me see if I actually have my, oh, I don't have my final answer. So remember, we found x and we found y. So x is just this part right here, and y is right here. That's my poster. That's not including the frame. The question is asking me, find the overall dimensions that minimize the area of the entire poster. So now I need to say my overall dimensions. I got to add in the border. So always go back and make sure you're actually answering the full question. So for the x, it's 7.071, but I need to add 4 to that, right? So here, there's the x plus 4. So it would be 11.071 inches by, and then I'm going to take the y and I'm going to add 8 to it. So that would be 22.142 inches. So that's the overall dimensions of the entire poster and the frame together. All right, that was a fun one. Ooh, I love this one. I think I say that every time I see a new problem. All right, so find the point on y equals square root of x that is the minimum distance from 4, 0. So you guys know what the square root function looks like. It looks like this. And 4, 0 would be right about here, right? 1, 2, 3, 4. And we want to find the point on this function that is the minimum distance. So once again, minimum. We're optimizing. We're finding a minimum value from 4, 0. Okay, if you remember from geometry, we have a couple things in this problem to remember from geometry. Minimum distance takes place when something's at a perpendicular, which isn't really going to come into play in this problem, but I kind of want to do a little extension on it maybe, because I find that to be really cool. Compare derivative slopes. I don't know, I want to. But anyways, the thing we really need to remember from geometry is the distance formula, which was this guy. x1 minus x2 quantity squared plus y1 minus y2 quantity squared. All right, and we do have an x and we have a y. Thank you. And the x and y that we have is 4, 0. All righties. So I'm going to plug that in. I might as well take away some variables here. So I'm going to do 4 minus, now I'm going to take away, oopsies, look at that. I'm going to take away the subscript because I'm just down to 1x and 1y, so this makes it a little easier. Ooh, I don't even like that either. Why do I not like that? I don't want to have a negative. I'm going to plug into the second spot. So I'm going to do x minus 4 squared plus, and now I have y minus 0, which is why I changed it. So y minus 0 is just y. So I'm going to write this as y squared. Okay. It's an ugly looking one. We're still in 2 variables. We're probably gonna have to do some chain rule possibly. We'll talk about it, how we could avoid chain rule. I gotta get it down to 1 variable. I know that y is equal to the square root of x, so I'm gonna put that in here. So if I have the square root of x squared, it's just x. So this is equal to the square root. I'm gonna FOIL this. So this is x squared minus 4 minus 8x plus 16, and then here this is plus x, right? I've subbed in here. I just want to refresh your memory as to what I did. All right, combine like terms. X squared minus 7x plus 16 under the square root. So guys, there's nothing wrong here if you want to take the derivative and do the chain rule. In fact, I think I will do that with you over here. However, I do also just want to point out that the minimum distance here, if I squared both sides and got rid of the square root bar, the distance squared, when you square all the distances away, the minimum distance is still going to be the minimum distance squared. So there's a lot of people, a lot of smart mathematicians that argue, forget this whole square root thing, just find the minimum of the distance squared because it's still going to be the minimum of the whole thing. Right? If you have a bunch of, like, picture that. If you squared all the distances, the smallest one is still going to be the smallest one when you square them. So there's many people that say, well, forget that. Just square both sides and take the derivative of the squared distance, and you get 2x minus 7, and set that equal to 0. And you save yourself some work with the chain rule. And I'll show you over here how you're still going to get the right answer if you just take the derivative of the whole thing. But this is very easy to see that this is going to happen at, if I set the derivative equal to 0, it's going to happen at x equals 7 over 2. So my ordered pair is going to be 7 over 2 comma square root 7 over 2. So let's take a look at where that is. So it looks like it's right about here. And it does look like it might be perpendicular, aka those rules from geometry are coming into play. But that is the ordered pair that has the minimum distance from the point 40 that's on the function square root of x. So let's just come back over here. I'll just prove to you that you wouldn't be wrong if you had found the derivative using the chain rule. So it would be 1/2 x squared minus 7x plus 16 to the negative 1/2, follow up with the chain rule, times 2x minus 7. So the derivative is equal to, I'm going to clean this up. So 2x minus 7 is in the numerator. 2 square root x squared minus 7x plus 16 is in the denominator. We want to set the derivative equal to 0 and solve. Well, what is the first thing that happens? X squared. You want to multiply both sides by the denominator, and this whole thing's going to go away, right? And you're going to have 0 equals 2x minus 7. So once again, you're going to get x equals 7 over 2, and you're going to get the same exact answer. But I do like presenting this theory to you guys because you can really visualize, well, if I have all these distances from this one point and I square them all, the smallest one is still the smallest one when I square them. Just an easier way to kind of do this problem if we have another one of these come up in the future. Okay, one more. The cylinder. A manufacturer needs to design a cylindrical can. All right, let's draw a cylindrical can. I am the worst 3D. I'm telling you, like back when I used to teach geometry, I just felt so bad for my students. Like it just was, we're going to pretend that that's a beautiful cylinder right there. Okay, we'll just go with that. Okay. The can's going to hold 1,500 cubic centimeters of liquid, so that's the volume. Find the dimensions, radius, and height of the can that will minimize the amount of material used. Huh. That's surface area, isn't it? Okay, so I want to minimize the surface area, but the only thing I know is really about the volume. So the volume of a cylinder is pi r squared times the height, right? It's just a bunch of circles piled on top of each other. And then how many circles? Well, multiply by the height of those circles, and you're going to have the volume, right? You're finding the area of a bunch of circles and adding them up. That's what volume is. Whereas surface area, well, we have a top and a bottom, so that's 2 circles. So that's 2 pi r squared. And then it's a very similar idea about using the height, but we don't care about the inside part. We just care about the circumference, right? So plus 2 pi r times the height, right? The circumference is 2 pi r. And then over here it was 2 pi r squared because the pi r squared was the area, but we have 2 circles, a top and a bottom. Okay, we want to minimize this, right? We don't want to waste any product. But we do know that the volume is 1,500 cubic centimeters. All right, so we have R, and we have 1H. I'm going to solve for H and sub in. Pi r squared. All right, so let's do this. So the surface area is equal to 2 pi r squared plus 2. I'm going to simplify this. And then this will be, it's going to cancel. It's actually not as ugly as it looks. What's that, 3,000 over r? So you could write 3,000 r to the negative 1 if you want. Is that what I did? That's not what I did, but you could. I'll do r to the negative 1. Hopefully you guys are okay with that move right there. The pi canceled, one of the r's canceled, so we were left with 3,000 r to the negative 1. All right, I am ready to take the derivative of this. So I want to minimize the amount of material used. So I'm going to find the derivative and set it equal to 0. So that's 4 pi r. Remember, pi is just a constant. It's not a variable. It's just a coefficient in front. Minus 3,000 times r to the negative 2. So I'm going to put that as r squared in the denominator. All right. I want to know, where is this equal to 0? So clearly I'm solving for r first, but I'm pretty sure if I go back and look at the original question, it asked me to find the radius and the height. So we're going to have to find both. So 3,000 over r squared equals 4 pi r. I'm going to come over here. I'm going to multiply by r squared. So I have 3,000 equals 4 pi r cubed. R cubed is equal to 3,000 over 4 pi. So you're going to use a calculator here. And guys, just be careful. When you take the cube root, make sure you put the 4 pi in parentheses, because if the calculator doesn't see it in parentheses, it's going to divide by 4 and then multiply by pi. Okay, so I'm going to do it in my calculator right now. I'm going to take the cube root of everything. So cube root, I'm just going to raise it to the 1/3 power. So I do 3,000 divided by, now I'm doing parentheses 4 pi. Oh, I should have done parentheses in the very beginning too, to show I want the whole thing raised to the 1/3 power. And I'm getting, so you get a completely different answer if you forgot those parentheses. So I'm getting that the radius to minimize the amount of material used should be 6.204. And that's centimeters. And now I'm going to plug that back in over here and find out what the height would be in this scenario. 1,500 divided by, and I'm going to put this in parentheses too. So I'll do answer squared times pi. And I'm getting 12.407 for my height. Cool. Very straightforward problems, guys. And again, you did problems like this in Algebra 1. I hope you did, in Algebra 1 and Algebra 2. And now we're just kind of applying the beauty of calculus to it. And that's it. So tomorrow's going to be a practice day between particle motion, mean value theorem, and this. Out of those 3 topics, this is my least, not my least favorite, but just the least important in general. The other 2, they're just much more important in the calculus world. So this, as much as it is fun, we won't be doing a ton of optimization problems. It's probably something I'm going to cut a little short this year just to catch up on some time. I'm about a week behind where I was last year. All right, but I will see you guys tomorrow. I think I did post some homework. Let me No, I didn't post any homework. You just have to watch the video today. Look at you guys. Oh, there's a Google form for you guys to do. All right, I'll talk to you later. Have a good day.